These are the first three letters of the Greek alphabet. And the third one is gamma, and you know that one best because that's what happened to the two of them come off, right? They decay. The alpha particle goes shooting off somewhere. So, first of all, what is radiation? It's nothing more than when something is emitted from the nucleus of an atom. Okay, and the key word there is nucleus. And so it could be particles or energy coming out of the nucleus. And we will only talk about nuclear reactions really for a short time. Most of chemistry, we're not talking about the nucleus. We're dealing with the electrons and the outside of the atom. So nuclear chemistry, the difference in nuclear reactions and chemical reactions is that very word right there, nucleus. So if a change in the nucleus is involved, it is a nuclear reaction. All right, first of all, radioactive decay. What do you think decay is? It's when something's breaking down. So that's really what happens in a decay reaction, what we call radioactive decay. And isotopes that are unstable, and let me just emphasize that word there, unstable isotopes, they become stable when they emit radiation. Okay, so what types of decay will we be talking about? One is alpha, and you know that symbol alpha there. The next one is beta. These are the first three letters of the Greek alphabet. And the third one is gamma, and you know that one best because that's what happened to the Hulk. The gamma rays got to him. So I know that's science fiction, but at least it helps you relate to what we're talking about. So let's get into these types of decay. So did you know that many elements are radioactive? In fact, some that occur naturally and some that are man-made. So radioactive elements begin with polonium, and everything from polonium on, if we continue here, of course, you know that this little section here jumps up in there. And so all of these elements right here are radioactive. So everything bigger than polonium. And there are a few other radioactive isotopes that occur naturally. So let's get into the three types of decay that you need to understand. First of all, alpha. The alpha symbol, you might see, I drew the little alpha, the Greek letter A. You might see it like that, or more likely you'll see it as a helium 4-2 particle. And so what an alpha particle is just two neutrons and two protons, which is basically the nucleus of a helium atom. Anyway, it's a small particle that comes out of a gigantic unstable radioisotope. So if you look at the ones that are radioactive, these are some really large atoms. And so it has a really big nucleus with a lot of particles that they are often unstable. Its penetrating ability is not that great. It can be stopped with a piece of paper and so forth. So I want to draw for you a radioactive decay reaction because you need to learn how to do this. I'm going to just start with a radioisotope of uranium-238. Okay, so you should be able to do this with any isotope. So I'm going to start with this. This is often what's called the parent, and then we're going to decay and then make the daughter. And so we will first write the alpha particle. Okay, so we have this big isotope, and then this alpha particle comes off. Now, what you need to learn to do is write what's left over. So we can actually just look at the numbers here. So we start off with 92 protons. Two of them come off, right? They decay. The alpha particle goes shooting off somewhere. How many protons are left? 90. It's pretty easy, right? Let's do the same thing across the top. Remember, the top is the mass number, which is protons and neutrons combined. And so let's do the same thing. We have 238 total particles. 4 fly off in this alpha particle, and we're left with 234, right? Because we can't lose any of these particles. Now, what we do is we take the periodic table and say, well, what is element number 90? Because it looks like we changed, right? We had 92 protons. Now that we have 90, we're a new element. And so element number 90 is thorium. Okay, and so that became thorium. All right, that is alpha decay. Now let's do beta decay. The example I want to do with beta decay is radium. So we'll start off with radium 228, and it's got 88 protons, okay? And so let's lose our beta particle. Now, the beta particle is really weird looking. It's a beta. I'm good with that. It's got a 0 and a -1. Okay, so what is a -1? How do you have a -1 particle? Because it looks like in our symbol that is the number of protons. So a beta particle is an electron coming out of the nucleus. And that should disturb you because you know that electrons aren't in the nucleus, they're in the cloud, right? And so what happens is a neutron kind of morphs into a proton and an electron, we'll say. So let's do the math here on the bottom, just the same way we did it on the top. So 88 equals -1 plus what? 89. And then on the top, 228 equals 0 plus 228. And so what we became is AC. Now, here's the deal. Notice that we increased by a proton. Where did it come from? One of our neutrons that was originally in our 228 morphed into a proton and an electron, and that electron was what was emitted as a particle. All right, the last one is super easy, gamma. So if we start with a radioisotope of TC99, okay, and we emit, I'm sorry, not TU, it's TC, and we emit gamma rays. Now, gamma rays aren't particles at all. They're just waves. It's gamma radiation. They are just waves. And so we can just put our gamma particle, and guess what it becomes? It's the same thing. Okay, all it did was lose a bunch of energy with gamma rays. Now, gamma rays, really short wavelength, really high energy. I mean, you know what it did to the Hulk, right? So they're actually quite dangerous, but that is gamma radiation. If you wanted to stop gamma radiation, you would need something more like layers of lead and concrete and so forth.